All right, on that optimistic note, let us get going with the optimal control for real this time. So previous 3 lectures were preparations. Now we actually do the blasted thing. So item 1 is general settings, right? So setup, general setup of an optimal control problem. What we're going to have is some instrument and some quantum mechanical system inside it. And the system is going to satisfy either Schrödinger's equation if we are dealing with a single quantum system, or Liouville von Neumann's equation if we're dealing with an ensemble. But substantially mathematically they would look identical, because we've got d psi by dt minus I h psi for Schrödinger's equation for the wave function. But remember Liouville von Neumann's equation, it was d rho by dt was minus I, and then the Hamiltonian commutation superoperator, so double hat acting on rho, and that's the same thing as minus I h commutator rho. What's important about this form, in the jargon this is called Liouville space. After some similar mechanics mathematics by Joseph Liouville, is that this and this to a computer look identical. Right? That's a matrix acting on a vector for a spin, and you can stretch a density matrix into a vector vertically, in which case that also becomes just a matrix, very sparse. And so mathematical setting of this and this is identical, and so we will simply today use the Schrödinger formulation on the understanding that if you ever have an ensemble or dissipative dynamics, you just stick the Hamiltonian and the relaxation superoperator in there, and the dimension of these is a bit higher, but substantially it is the same math. Okay, now what we have in our system is the total Hamiltonian. We will partition it into the part that we cannot control, J couplings, chemical shifts, various detunings in laser physics that we cannot easily move, shift, or in any way influence. And then we will add to it the part which we can control. And I've given you a couple of examples in the previous lecture where we could have either electric or magnetic fields or both that we can alter by changing currents through the various coils, for example. And so we will have a sum here, and I will match the notation to the handout, so sum over n, then with some coefficients that the instrument can vary, so there will be Cn as a function of time, and then some operators which the instrument can actually put out. For example, magnetic fields, but we will just call them Hn, and those will be our control operators. And here goes from 1 to the number of control channels that we have. And to give you an example, in a typical protein and a mass spectroscopy context, that will be all the chemical shifts and J couplings, and these will be the Zeeman interaction operators Lx and Ly on separately protons, carbons, and nitrogen. So you would have 6 control channels in here that we can independently vary. So the names, that's called the drift Hamiltonian. These are control coefficients, or waveform in the jargon. And these are control generators. And then the word generators comes from our first lecture. Remember, in the Lie algebras, when we dealt with the exponential map from the Lie group, from the Lie algebra to the Lie group, the linear combination of the operators whose commutators were generating the Lie algebra were called generators of the corresponding group action. So this we inherited from the mathematicians. Okay, now we have to put this into our Schrödinger's equation, but it's not just that. We would in practice have a number of constraints. So item 2 here is constraints and penalties. If you have a patient in an MRI machine, there are strict limits on the power deposition in human tissue. Although magnetic resonance imaging is a magnetic technique, of course, any electromagnetic field also comes with the electric component. Tissues are conductive. What will happen is the electric field will jitter the ions around and hit the tissue. You do not want to cook your patient inside the MRI machine, and so there are penalties on the maximum amplitude of what you're allowed to dump into tissues. So, types of those constraints and penalties. So, A, max amplitude. Right, we might not be able to exceed a certain threshold. B, max frequency. Our instrument might not be good enough to output certain frequencies, particularly in electron spin resonance, where the Zeeman frequencies of the electrons can be in the hundreds of gigahertz, and it's exceedingly difficult to output those frequencies in a controllable way. Then there may be other things. There may be, for example, running cost. So C, running cost. It may well be that your amplifier can actually survive a certain maximum amplitude, just not all of the time. So if you are hitting a particular transistor or a particular diode inside it, the amount of hits that it can dump into whatever's cooling it over time is limited. And so there would be things like this. If we have an integral from 0 to the experiment time, there will be some cost function, lambda of t, that is weighing one of these control coefficients, so Cn of t dt. So that is one possible form of a running cost, that with some coefficients we are summing up the totality of what we have dumped into the system, and there may be limits on that. We may simply just not like high amplitudes, right? So D, so penalty on amplitude. And that can look like this. For example, we can have an integral from 0 to the duration of the experiment, Cn of t absolute square dt. So that is related to the total power that we have expended in the experiment, and we might want to drive that to a minimum. Okay, so we have our evolution generator here with our controls. We have the penalties of whatever kind that we must observe and avoid and respect in various ways. So how do we put that and that together? Well, let's think about it. If we have our initial condition, psi naught, or some initial density matrix in which we are starting, then we will have our experiment that runs there, and that's just the Hamiltonian as a function of time. So we would have h of t in here. Then what we put here is the total aggregate propagator of our experiment. So all of these Hamiltonian instances. And what is going to happen in there is there will be, it's a somewhat weird notation, so it's called a time-ordered integral, so x minus I integral from 0 to t, h of t dt. And I will explain to you in a moment what that is. Those of you who did quantum physics would probably recognize Dyson time order propagator, but for our purposes here, it's just a very fancy way of saying run the entire experiment on this initial condition. And then, of course, at the end of this, we would like the system to be in some particular specific destination state. And let's put it in here, and we could call it phi. And not only that, we would like it to be in that destination state in some specific phase, right? Typically 0. We don't want any phase multipliers that have arrived into here because they are, well, a mess. And so we probably just want the real part of that. And what we do want for that real part is to be maximized. So we declare something called fidelity. Omega, big, and if our experiment is successful, so it does take our initial condition literally precisely into phi, then this inner product is going to be equal to 1. The real part will have no effect, and this will be equal to 1. If our experiment is awful, we will end up somewhere other than phi, and then this inner product is going to be small and probably complex, at which point the real part will make it even smaller, and then this is small, and so our job is to maximize this, right? The bigger it is, the better we are doing, and the maximum, because of normalization condition, is equal to 1. But we must have all of this in place, and what we can simply say here is, okay, there will be some penalty, and we will call it J. And this will be, in some general sense, a functional of all of these control sequences that we have here. So of C and of T. And that simply says that whatever it is that this functional is doing to them, as per the discussion here, it is doing. And then the worse we are at observing those penalties, the greater this number is, and so we subtract that number from the fidelity. So then, depending on the relative weights of these and these, we can adjust coefficients inside J to regulate the importance of different penalties and to what extent we allow the instrument to ignore them. We then need to maximize this. So these are called fidelities, fidelity, and that is called a penalty. And one important thing to remember, and that's a product of practical experience with optimization theory, is of course we could have put hard constraints on the control sequence. Just say, okay, if the optimizer hits a certain threshold, we do not allow the waveform to go above that. That's a bad idea because it's not compatible with the convex optimizers, right? It will just keep trying, and if you're just clipping the gradient, it will get stuck. And so rather than imposing hard penalties on hard boundaries on your waveform, it is much better to put them as continuous differentiable penalties, because then the optimizer has first and second derivative information about them, and it can intelligently avoid them rather than just get stuck at some clipping point if you have a hard boundary in place. So penalties are better than constraints in all of these cases. Okay, item 3. So what we now need to do is we need to discretize the time, because as you can plainly tell from here, and if you look in the textbooks on the definition of Dyson ordered time propagator, it's an absolute horror. So running this stuff in continuous time is inconvenient, and so now we discretize time. So time discretization. And for that, I need the form of this solution, which I have derived to you a few lectures ago. So we have psi of t plus dt, so infinitesimal increment of time is e the minus I h t dt, and then this is psi of t. So if our time increment is infinitesimally small, then this is exact. Right? However, in practice, what we want is we want our dt to be some finite time increment. And typically in magnetic resonance, the instrument can actually literally output piecewise constant Hamiltonians. In other spectroscopy, it's an approximation. But what we say is, okay, we now discretize our time into little intervals, and we will call those intervals delta tk with centers at the points that we will call tk. So we can then rewrite this like that. Psi of t plus delta t will be e minus I h t. Now we are now at a particular time tk, then delta t and the width of that interval tk, then psi of tk, and that is tk plus delta tk. So what this means graphically is previously our Hamiltonian depended on time in some continuous way. So if we notionally, of course it's a matrix, right? But if we just notionally say h, and that is t, what we previously had was some continuous time dependence. What we now have is discrete intervals like that. Not necessarily all of the same width, and then they are piecewise constant in here. So draw it like that, that, and then this, etc. So the width of each slice in here is delta tk. The time of each slice here is tk, and that discretizes our problem. And of course, in the limit of infinitesimally thin slice, we will converge to the exact solution. And the meaning of infinitesimally thin physically in this context is that the system shouldn't evolve too much within each slice, and the practical recipe for this is you reduce the slice width until your answer stops changing. So just see convergence numerically. Funnily enough, NMR spectrometers, because we're dealing with radio frequencies in there, Anu's already seen it in the experimental work, they can literally output piecewise constant waveforms, in which case this is not even an approximation. Right? But EPR instruments would not be able to because of time constraints, and so sometimes it is approximation and sometimes it isn't. Okay, so what we'll do is we will say fine, within this slice, so our Hamiltonian is called HK, and it will contain, much like we defined here, the drift part, and it is the same at all time slices. So we will have H not the drift, and then it will have this, but now we are discretized, so this becomes Cn of Tk, and what I'll do is I'll say, okay, Cn at Tk will be Cnk, right? The case time point of the nth control channel. And we put it in there. So we have a sum over all control channels, n1 to n. Then we will have the coefficient of that channel at that time times the corresponding control generator. Okay, and we have a time delta t in which to evolve. So, because the Hamiltonian is now to be constant, assumed constant within that interval, we can actually calculate the corresponding propagator. So the propagator of that interval, and I will call it pk, will be the matrix exponential minus I And then we have this Hamiltonian H naught plus a sum n1 to n c k n h n. And then we have delta t k in here. So that propagates us through the kth time slice. Okay, now we know this. We know this, we know this. This was given to us by the user. We can actually calculate this exponential. We can just tell MATLAB, okay, do that. And it will do it, and then we will be able to evolve our initial condition. Fine. Let us number these slices. So that will be slice 1, slice 2, slice 3, and so on. To slice, and let me make sure I do not mess up any other notation in here, say slice M. Okay, let's think what happens. We have our initial condition, psi naught, then the instrument arrives at the slice number 1, which has this particular Hamiltonian for k equals 1. We put it in here. We know the width of that slice, it's delta t1. We compute the exponential, that's our p1, propagator number 1, acting on our system. Fine, that evolves the system from the start here till the edge of this slice, at which point the instrument switches the control amplitudes, and we are now in the slice number 2. Exactly the same process, P2. And you can see what happens in here, right? Initial condition propagates through first slice, propagates through the second slice, dot, 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 propagates through m minus first, propagates through m's slice, and at that point, we would like to have arrived at our chosen destination. So that would be phi. And we take the real part of it, and we would like that to be maximized. Now, how do we maximize things, and what are we maximizing it with respect to here? So let's not worry about the penalties. Penalties are typically easily differentiable functions. So you can just, this is not quantum mechanics, this is just, you know, whatever it is we are not allowed to exceed. By how much? But let's think about what we are optimizing with respect to here. Well, the only thing we can control are really these coefficients, right? That's been given to us by nature, that's been given to us by chemists, and so we can only control these. And so this omega is in fact a function of all of these CKs and all of these control channels. If we have 1,000 time steps with 6 control channels, there will be 6,000 elements in here, and we have a 6,000 dimensional optimization, I'm afraid. And this is why this entire subject is only flourishing now, because now we have big enough computers to actually handle that stuff. Okay. How do we optimize? Well, for example, by gradient descent. And for that, we need gradients. So, next item on our agenda is the famous algorithm called gradient ascent pulse engineering, GRAPE. Now, that was a proper revolution at the time. There was a paper by Navin Kaneja, Thomas Schulte-Hebruggen, Stefan Glaser, and Cindy Cayley, I think, in the early 2000s, where they found an algorithm that calculates the gradient of that monster surprisingly cheaply, at the cost, more or less, of just 2 time propagations, plus or minus a little bit of logistics. And previously, of course, people had to numerically differentiate the entire simulation with respect to 6,000 or thereabouts parameters. That's a bit painful if you do it numerically. So let us take a look at what this thing is about. So, as per our conclusion there, what we want is d fidelity by d c k n. So we want the derivative of the fidelity with respect to the amplitude of the nth control channel at the time slice k, and If we have a positive derivative, we go in that direction. If we have a negative derivative, we go in the opposite direction. That basically gives us the direction in which we have to alter this coefficient in order for the fidelity to grow. Right? Standard process of gradient ascent. Of course, since it's been a bit more sophisticated, but there we go. So we want that. Okay, let's do that. D by dck n of our entire thing there. I will drop the real part for now for convenience. It's exactly the same in complex arithmetic. We can take the real part later. Okay, find the destination state, then propagator at slice m, propagator at slice m minus 1, and so on. At some point we will encounter slice k. Pk, and then P2, P1, and then the initial condition. But let's think about which part of this depends on Ckn. Well, it's just the case propagator, right? Because it doesn't care what was before, what was after. That's the coefficient specifically in the case slice in here. And product rule applies always, right? Most of quantum mechanics is associative, and so if all of that doesn't depend on this variable, we can simply take it out of the derivative. And so what this ends up being is phi pm minus 1, and then dpk by dckn, and so on, P2, P1, sign out. So we simply just need the derivative of one propagator with respect to this. And this makes the algorithm extremely efficient. Think about what we're doing here. That is a piece of the system trajectory, forward trajectory. We start from the initial condition, click forward, click forward, click forward, click forward. So this is forward trajectory. That we can interpret as the initial condition evolving backwards in time. All right, pm minus 1, so we're sitting here and we're going backwards. So this is backward trajectory. And of course, what we're going to have is some state here and some state there, and that's just a single inner product with this derivative of the propagator. And so what we need to do realistically is calculate one complete forward trajectory, one complete backward trajectory, and a bunch of these derivatives, and take a bunch of inner products, and we will have the entire gradient at the cost, more or less, here of running the simulation twice, once forward, once backward, and a bunch of things in the middle and a bunch of inner products, which are surprisingly cheap, as you will see in a moment. And so that's the famous GRAPE revolution, that suddenly the expense of computing these gradients from astronomical went to something that people could do on a laptop for pretty significantly sized spin systems. So long as you can store all of these matrices to begin with, you can do GRAPE on them. Okay. So our next mission is to find out how to calculate these derivatives. And I will remind you what it is. So our pk is this monster here. It's a matrix exponential, and how would one differentiate a matrix exponential with respect to a parameter? And so that's our next item. Propagator derivatives, and that I think is number 5. And let's just say that we have a Hamiltonian that depends on a certain parameter, h of alpha. For simplicity, because we really don't want to rewrite this entire monster every time. So we simply have a Hamiltonian, and that Hamiltonian simply depends on some parameter. what we need to do is to differentiate the corresponding exponential with respect to alpha. So we want d by d alpha of e minus I h delta t. That we need to find out. And as you can imagine, this is not as simple as doing the chain rule in this case. Chain rule sometimes doesn't work in quantum mechanics because things don't necessarily commute. And this is one of those cases. So we cannot do the straight chain rule here. So we need to be, somewhat more creative and somewhat more precise. So methods for doing that. In the early days, what we could simply do is, for example, finite differences. Right? We could say, okay, let's call this P. So P of alpha, that's P prime of alpha, is that. So we could say, okay, P prime of alpha is approximately equal, as we are used to from our numerical computing courses, of P of alpha plus h minus P of alpha minus h divided by 2h, a finite difference approximation here, where because of the accuracy conditions on this, I will not derive the residual for this and so on. The good choice of h is the square root of machine precision. So this has got quadratic complexity, and if you put the machine precision increment in there, then the accuracy will be a multiple of machine precision, which is what you realistically typically need. But this is painful because you need to compute matrix exponentials twice. In this case, it is perilous because in a lot of cases these Hamiltonians will be badly conditioned. They will have giant terms in them, like Zeeman interaction in the hundreds of gigahertz, simultaneously with tiny terms like J couplings, which will be 10 or 20 hertz. And so then your increment here might be small compared to the Zeeman interaction, but might be giant compared to J coupling at the same time. And so there are numerical accuracy problems with such things, and in practice they're only used for debugging these cases. So avoid if possible, and only use for pretty much just unit testing, right? If you are computing the derivative somehow, testing it against finite differences is in fact the recommended strategy, and it's implemented in MATLAB automatically. You can in some cases just tell it, okay, test this before you use it against some reasonable finite difference. The second approach would make use of the fact that this P is, matrix exponential that has a Taylor series. So we would have that sum n0 to infinity minus I delta t to the power n over n factorial, and then h of alpha to the power n. And we need to differentiate that with respect to alpha. Here is the problem, is that the usual rule for differentiating powers no longer works, because the Hamiltonian might not commute with its own derivative. So we need to use only that rule over there, and so we must expand this. It's a sum n0 to infinity minus I delta t to the power n over n factorial, and then this is h, 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 and that is n times prime alpha. And then when we differentiate that, okay, so it's the h derivative times the rest of them, it's h times h derivative times the rest of them, then h times h derivative times the rest of them. So that is going to be sum n0 to infinity minus I delta t to the n over n factorial, and then another sum L equals 1 to the number of terms in here, to n, and then we will have H and H prime alpha, and then H, where this occurs in position L of that product. Now, I will not derive this, see the book, but a giant amount of reordering and simplification. So dot, 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 and that dot, dot, dot is about an hour long. That can be recast as a Taylor series in commutators. So what we can have here is exp minus I H delta t, and then there is a sum of m0 to infinity minus I delta t to the power m over m factorial, and then we have m-fold nested commutator of H itself with the H prime alpha m-fold nested commutator. I will not bore you with how that is obtained, but that is a somewhat better way of doing that because the accuracy is strictly controllable. You can continue summing until the subsequent terms become smaller than machine precision or a certain threshold, and at that point you stop. But this is still, monstrosity. Too much effort. So what is being done these days, and I'm giving this to you for historical and debugging purposes, is a relation that, again, we don't have the time to derive here, but which has resolved all of these complications instantaneously. It's relatively recent, but for any matrix, so if we call it just A, so A 0, A dA by d alpha, that is e to the a d e to the a by d alpha 0 e to the a. Now that takes a little bit of parsing and a certain amount of credulity to really believe, but that is true. If you have any matrix A whatsoever, square matrix, and it depends on some parameter alpha, and it can be differentiated with respect to that parameter at some point. Of course, the derivative will also be a matrix of the same size. You create a block matrix like this, so you put A into that block, derivative into this block, a 0 block here, and again an A here. You exponentiate that entire thing, and magically, the derivative of the matrix exponential turns up in the top right corner. This is called an auxiliary matrix, AUXMAT, and this is how propagator derivatives are calculated these days. Of course, dA by d alpha in our specific context here will just be one of these control operators, right? And A will be the full propagator at that particular slice. So that then simplifies this process enormously, because each of these propagators is just the exponential of the Hamiltonian, and then this derivative is an exponential of that bigger thing, and you take the corner block out of it and put it there. So that gets us the gradient. So we now know the gradient of omega, and that is a good thing because we can now start optimizing. And there are various ways of optimizing that stuff, and this is why I have been boring you with molecular geometry optimization in the first half of this course, because all of those methods, gradient descent, quasi-Newton, Newton-Raphson, regularized Newton-Raphson, and so on, are now deployable in this context. So what we can do is, of course, firstly, we can just use the straight gradient descent. We can take the entire vector or matrix of those coefficients And our j plus first iteration of the optimization will be our j's iteration, and we want to go up the gradient, so that's plus some step length alpha, let's call it something else, lambda, and then the gradient of the fidelity with respect to this control sequence. And with a suitable choice of lambda at each step, we will be moving closer and closer to the maximum of the fidelity. That is the original suggestion in the GRAPE. Of course, what we can do instead is we could say, well, okay, we have our Cj plus 1 is Cj plus or minus, I don't even remember, check in the derivation, but the inverse of the Hessian, and in this case that's the Hessian matrix, not the Hamiltonian, times the gradient, so that would be the Newton-Raphson method for that. And if we are using the history of the gradients to get the approximation for this Hessian at every step, that is your quasi-Newton, for example, LBFGS. Right? So we can get there, and LBFGS, quasi-Newton method, etc. There are plenty of optimizers, some better than others, some more adapted for specific contexts than others, but that's the general idea. So I think that is more or less what I wanted to say here. We will go into further particulars and specifics in the next lecture, but substantially here what we have is either a quantum system obeying Schrödinger's equation or an ensemble of quantum systems obeying Schrödinger-like form called the Liouville space of Liouville-von Neumann equation for the density matrix. Mathematicians call it a joint representation. And then in there, so our evolution generator, either the Hamiltonian here or its commutation superoperator there, will contain the part that we cannot control, called the drift, will contain the control generators. These will be the Zeeman operators for spin and the electric field operator for the electric field dot dipole moment operator for laser control. Then that's our control waveform that the instrument can generate, usually subject to a pile of penalties and constraints, which we can either enforce separately or put them into the overall figure of merit in here. And our figure of merit is the extent to which our system arrives from its initial condition to some destination state that we would like to hit. That is the full experiment propagator. We go from the initial condition, we arrive here, we take the inner product with the destination state. If this number is large, we are doing well. If this number is small, we are not doing well, so we need to maximize it. Before we maximize it, we need to discretize time. And we say, okay, we know the solution for this, that when the Hamiltonian is piecewise constant. In fact, the exact version with infinitesimal time steps looks like that. And we can discretize it further and say, okay, if we assume that our Hamiltonian remains constant in some thin slice of length delta t, then our next wave function at the edge of the slice is related to the previous wave function at the edge of the preceding slice by this equation. And that is something we can directly compute because we know what the Hamiltonian is at each time, and that's called the propagator, as you've already seen in the previous lecture. And if I open that up with the structure of the Hamiltonian, which we have discussed here, I will get this, and the control on the channel n at time k will just be a number. Okay, with that in place, we start evolving our quantum system through the first slice, through the second slice, and they are just acting as operators, and they move the system forward in time. Project it onto the destination state, take the real part, maximize this. How do we maximize? Convex, or well, at least smooth and differentiable functions. We want the gradient. We write the gradient down. We realize that the only part of this entire long chain of events that even depends on C and K is the case propagator in here. And we pull the derivative in towards that propagator. So we now need to calculate the derivative of a matrix exponential with respect to something it depends on. And that can be done in a variety of ways. And the worst way is to do finite differences. The second worst way is to sum up the Taylor series. If you look at the original GRAPE paper, they are actually truncating this Taylor series at the first term, which also has implications. If your delta t is too long, then that approximation breaks. But if you sum up to infinity, then it always works. But still, this is either a nasty double summation, one of the sums goes to infinity, or a nasty commutator series, a bit of a pain to calculate. So that was in spinach at some point as an option, but we then took it out as soon as we fully deployed that, because of course matrix exponentiation is an elementary operation in MATLAB, as you know, and you can simply concatenate matrices just by putting them next to each other in a text file. So concatenating, exponentiating, and extracting a corner block is literally 2 lines of MATLAB. Like 3. Make the matrix, exponentiate, and extract the block. So compared to that horror, that's a serious improvement. So this is now the dominant method that we have there. That gets us the derivatives here. With the derivatives, we can calculate all of the individual derivatives here. That gives us the complete gradient of the fidelity with respect to the control sequence. Gradient is the steepest ascent direction. If we step in that direction, we are guaranteed, at least for some step, to increase our fidelity. If we just step with some carefully chosen step, that's the straight gradient descent. If we do it like that, that's Newton-Raphson. In principle, we can also put a step in there, do a line search in the predicted descent direction. That is what spinach is actually doing these days. Or we can fudge the Hessians and do the BFGS type approximations to it, which is a lot more efficient because this only needs first derivatives and that needs second derivatives. They can be computed in a similar way, but it's a bit more problematic. Read Uluk's paper on the subject of how to do all of that through. Okay, that I think is what I wanted to say on the subject. There are 3 of you sitting here who will need that. So Maxi, Callum, and Jenna. The rest of you is optional. The 2 of you already know all of this. So yeah, it will take a bit of getting used to. Well, look.
Usually at each time step, does the H0 drift have more impact than the control channel?
Depends. It may be much bigger than the controls in some spectroscopies, or it could be much smaller. For example, if you have zero field NMR instrument, which specifically screens out even the Earth's magnetic field, so the magnetic field is precisely 0, then you have no chemical shift. And that usually is what dominates. Then your J coupling is like 20 Hertz, but your control could be 20 kilohertz.
So if, let's say, if we turn off all controls and just simulate it with just a drift, if we're extremely unlucky and the drift has a very large impact, it may take us really far away and we might just not be able to get there with our controls.
Correct.
But
yeah.
If the drift is near 0, we're limited by how far our controls can take us. Because they'll be by 1 minus 1.
Yep, that's a matter called controllability and reachability, and that's the next lecture.
Okay.
Anna.
In the optimum structure, when you're specifying the penalties, it is just a number, right?
It's the coefficient in front of J.
So, okay, so it's like if it's 0.01, we're saying take 1% of the penalty that we specify. Okay.
So there's a library of penalties corresponding to all of that, and what you specify in spinach is the coefficient in front of this.
Yeah, okay.
Yeah. Right, see you next week.